Hello, everyone. Welcome to the video session for Lab 4, which is on the MOSFET. So we are going to talk about the instructions about this lab, and we are going to discuss how you can complete this lab and what are the tasks on it. So in this lab, we are going to work on MOSFET devices. And in the first part, I'm going to go over these device characteristics and what we are trying to analyze for these MOSFETs. And then later on, I'll show you how to actually simulate it in your LT-SPICE and then what the experiments are that you're going to run. So first, let us start with the MOSFET device. So the name of this device comes from metal oxide silicon field effect transistor. These devices are built on silicon substrate, and then we have different P-type and N-type regions inside them. And there is a metal and metal oxide layer on top of the device that actually creates the effect of that is called field effect. And that's how they are built. So there can be two types of MOSFETs. One is called N-channel MOSFET, or in short, we call it NMOS. And the other one is a P-channel MOSFET. In other words, in short, we call them PMOS. So we are going to analyze both of these MOSFETs, N-type NMOS and P-type PMOS, and find out what their characteristics are and analyze them in terms of device characteristics and find the values for them. So let me draw the device first in a 3D diagram so that you can get an idea of how they're actually built. Then I'll draw a 2D diagram during our circuit or device analysis. So this is a silicon substrate that is actually the basis of this device. So the silicon substrate, if we are talking about the N-channel MOSFET, then we are going to go over that with respect to that, and then we are going to talk about the structure of the P-channel MOSFET. So the N-channel MOSFET, it usually has a P subtype doped substrate. Which is doped up to 10 to the power 16 or 10 to the power 17 atoms per centimeter cube. And then inside this device, inside this substrate, we have two regions that are doped with N-type dopant. And then we are calling it N plus because those are heavily doped compared to the P-type doped substrate. And on this side, let's call it source region. And this region, let's call it drain region. So in MOSFET devices, the sources and drains can be interchangeably used. So you can basically use them either way. But for our purposes and discussion, we will choose this as a source and we'll choose this one as the drain. And in between them, on top of the MOSFET, we have one layer of insulation, which is usually called gate oxide. Could you try again? Which is called a gate oxide or silicon dioxide in this layer, like a thin layer of gate oxide above this device. And then on top of it, we have another layer, which is a polysilicon. Ideally, they use a metal, they used to use a metal layer over here, but now in the modern devices, they use polysilicon, which is a heavily doped silicon layer, which basically works in place of a metal, like it conducts and stores charges pretty easily. Um, So these are our three of the terminals. So this is source, this is drain, and this top terminal, the polysilicon terminal, this is called gate. And then the substrate is usually either called substrate or you can call it body. So these are the four terminals of these N-channel MOSFET devices. And then you have, if you consider that if you have a P-channel MOSFET, then all the areas will flip. So I'm going to draw that layer now. So for the P-channel MOSFET, what you have is an N-type doped substrate or body. Then you have a P-type, P plus doped source and a P plus doped drain. On top of it, you have again a silicon oxide, a silicon dioxide insulation layer. And on top of it, you have a polysilicon gate layer. Yeah. So you can call this as a P-channel MOSFET or PMOS. And it has the same name for the terminal, gate, body, source, and drain. So we are for our analysis, we are just going to focus on NMOSes first, and then we can move on to the analysis to the PMOS side. So for the NMOS, we are basically dealing with this structure. I am going to draw it in a 2D manner as a cross section so that we can see all the layers. And in the first part, we are basically going to show how these devices are formed. So when you have a P-type substrate and N plus region for sources and drain in these two areas, we basically create two diodes and two PN junction diode, one over here and another over here. So to make this operation, to make this MOSFET operate correctly, we have to always make these two diodes in reverse bias operation. So we do not want any kind of current to flow from the body up to the source or from body to the drain. So to ensure that, we have to always bias these two diodes in reverse bias condition. And to ensure that, we are going to uh, connect this body terminal to the lowest potential of your circuit. Usually that is the ground. If not, if you have a negative voltage node in your circuit system, then you have to tie that body terminal of the MOSFET or MOSFETs down to that potential. So for our discussion simplicity, we are just going to assume that ground is the lowest potential. So the first action will be to ground the body terminal so that these two MOSFETs are always, these two PN junctions are always reverse biased. So now you have your source over here and your drain over here. This is your insulation silicon dioxide gate oxide, and then you have the polysilicon gate on top. So once these two regions, PN junction regions, are reverse bias, we can assume that there is a depletion region that forms along the junction of the P-type and N-type region. And we already have seen this phenomenon in the diode operation. So it's similar to that, like how PN junction diode in the reverse bias zone has a wide depletion region forming around them. And then the p-type region will have hole carriers as a majority carrier, and a few very few electron carriers, which are the minority carriers. And the N plus regions will have a lot of electron carriers in both source and drain, because that's the doping concentration, uh, the result of the doping concentration. But you can see that whatever voltage we apply at the source or drain, there will be no way to have any current flow from these two, between these two N plus region. And that is the purpose of having this gate terminal, because that gate terminal voltage is going to control that channel, and it's going to create a channel between these uh, two N plus region, so that there can be a current flow between the drain and the source. And the way to do it is we are going to apply a positive voltage at the gate terminal. Let's call it VGS, because we are considering that that voltage is with respect to the source. And for our discussion for now, what we are going to do is we are going to connect the source terminal down to the body terminal, and that is already connected to ground, so that you don't have any, like the source connection is at the ground. So whatever voltage you apply at the gate terminal, that is the VGS voltage, where the source voltage is at 0. Um, so now if you apply a positive voltage at the gate terminal, that will create an accumulation of positive charges inside the polysilicon layer of the gate. And this polysilicon layer is insulated from the silicon substrate down below with this silicon dioxide gate oxide layer. But these accumulated charges, positive charges, are going to attract these minority electron carriers inside the p-type substrate, and those electron carriers are going to come up to the surface right below the silicon dioxide layer. And once you have enough charges, minority carrier electrons accumulated here, then you basically form a continuous channel of electrons that is working between the drain, that connects the drain region with the source region. And then there can be, if you apply a voltage at the uh, drain terminal, which is the positive voltage between the drain and the source terminal, then you can actually see a current flow, IDS, that flows from drain to source, and the electrons will flow from source to drain. So that is basically the overall operation of these devices. So we have established that these MOSFETs will have three different operating regions. The first one is the cutoff region, which is when you have 0 voltage at the VGS terminal, between VGS. Then your current is obviously going to be 0. Then as soon as you start to increase the voltage, you'll see the charges, electrons are getting accumulated in the channel, um, in the channel region. But the current is not going to flow right away. It's going to, similar to the diode, you will see that up to a certain gate voltage, there is no current. But once that gate voltage crosses a particular threshold, there will be a current flow between the drain and source. That voltage, which is required for any kind of MOSFET, is called threshold voltage. And it is a device parameter which is dependent or defined by the device physics. We are not going to go into too much detail on that. Just know that for NMOSes, this threshold voltage is a positive voltage. usually is between zero point 0.5 or zero point 0.4 to zero point 0.7 volt. And it is basically the voltage required at the gate that will overcome the accumulation that will create the accumulation in the channel region for the current IDS to flow. So the so as long as the voltage at the gate is lower than this threshold voltage, there will be the MOSFET will be in the cutoff region. So there will be no current flowing as long as the VGS is less than VTH. So we can rewrite this condition uh, at the cutoff as VGS less than VTH. Now the second region, when our VGS becomes larger than VTH, and we have a voltage VDS between the drain and the source, this region of operation is called triode or linear uh, region, and the condition is VGS is greater than V threshold and VDS is greater than 0 volt, but it is less than VGS minus V threshold. So as long as our drain to source voltage is within these two limits, we will have a linear current where the IDS is proportional to the voltage VGS minus VTH minus VDS by 2 into VDS. So we can rewrite that equation as IDS equals to Kn prime VGS minus VTH minus VDS by 2 into VDS. So the derivation of this equation is given in the textbook, and it will also be discussed in terms of physical like derivation in the theory. So you are most welcome to read through that and understand how we get to this current equation. But for the purpose of this lab, we are going to concern only on an abstract view, on a high level analysis of, you can clearly see that this current is proportional or dependent on these voltage terms that are between the gate and source, the threshold voltage, which is a device parameter, and then the voltage applied between the drain and source, VDS. And you can also see that there is a constant, a proportionality constant that comes here, which is Kn prime, which is called transconductance parameter. So this is the first parameter that we are going to analyze in this lab. This parameter is an inherent quality or characteristics of these devices. So for the NMOS and the PMOS, we will get a particular value of Kn prime. It is a device parameter, so every MOSFET will have some sort of transconductance parameter, which is basically the ratio of the drain to source current and the voltages, external and internal voltages of the MOSFET. So that's our first parameter term that we are going to find out. And then once you keep increasing the drain to source voltage VDS, we will move on to the third region of operation, and that will happen. Uh, Let me erase this part so that we can discuss that. So for that discussion, let's move on to that. So the third condition will be when VDS is greater than or equal to VGS minus VTH. At that condition, what happens is we see the current to become a saturated constant value. That's why this region of operation is called saturation. Once the MOSFET reaches that saturation value or saturation region, our current will become independent of the VDS. So it will not depend on the VDS value ideally. So the ideal equation of IDS will become Kn prime by 2 VGS minus VTH whole squared. But this as we are discussing the parameters, there is also another parameter that will come up now, which is called channel length modulation. And that term appears in the saturation region in terms of another constant, which is lambda times VDS. So that is how the IDS ideally is not supposed to be dependent on VDS. So even if we increase VDS value, it's supposed to be a constant. But here you can see clearly that IDS still depends partially on the VDS value via this lambda parameter. So lambda is called channel length modulation parameter. And this is again just like Kn prime. It's a device parameter, which happens more and more with uh, short channel devices. As we are shortening this channel length, we are seeing this phenomenon more prominent and more important to analyze. What happens is ideally our current curve is supposed to look like this. When you have IDS in your y-axis and VDS in your x-axis for a particular drain voltage, you are supposed to see a curve like this where the current is going to increase linearly in the linear region, and then up to a certain point when VDS becomes greater than or equal to VGS minus VTH, you will see a constant current as long as you increase VDS. But what we are seeing here, due to the channel length modulation, this current is going to increase, although it's a lower rate, but it is still going to increase with a slightly smaller slope. And that is going to replace this part of the curve. So even in saturation, the current is not going to stay um, constant. It's going to increase with a slight slope. And that slope will give you the value of the lambda, and that part of the um, derivation is also in the textbook. So you can read through that to understand it a little better, how to derive that from the plot. And the just what we discussed with the Kn prime value, which is the transconductance parameter, we can find that from the slope of in the linear region. So that those are like two of the parameters that we need to find. Now let's talk about the third parameter that is also there. So for our purpose of discussion, we assume that the source to body voltage is 0. And as long as that happens, we call this condition as um, zero biased body connection, because it's connected to ground and there is no uh, voltage difference between the source terminal and the body terminal. But oftentimes what you will see in large systems with MOSFETs, all of the body terminals of NMOSes will be tied to ground or the lowest potential of your circuit. But sometimes what happens is your source terminal will have a different voltage than the body terminal. It may be slightly above or uh, at a certain voltage point in the circuit where that is the voltage of the source terminal. And then essentially what you will have is you will have we can represent it with a voltage source here between the source and the body. And that is going to affect the threshold voltage of your device, because the threshold voltage basically indicates that the amount of voltage you need at the gate terminal to create the accumulation of these electrons between the source and the drain. But if you already have a body voltage applied to it, it sort of acts like an offset, and that will either increase or decrease the overall threshold voltage of this device. So the equation that dictates it, we can write it like this. V threshold is VT naught minus gamma root over VBS plus 2 phi F minus root over 2 phi F, bracket close. So you can see from this equation, as long as this VBS is 0, you see that the second term here is 0. So you get the zero bias threshold voltage, which is VT naught. But as soon as you have a voltage difference between the body and the source terminal, then you will have a positive term value here, positive term here minus this 2 phi f, which is obviously smaller than this term. Then you have a positive number that multiplies with this constant gamma. And this gamma is called the body effect parameter. And that is our third term that we are going to find out for this device. Due to that, you will have a different threshold voltage, VTH, than the VTO, like the zero bias body threshold voltage. So we have to find it for that. So, and this equation is particularly specific to the NMOS. So for PMOS, the only thing that changes is the sign here. And then the polarity of VBS will be reversed, so it will be VSB. So anyway, so that's basically our overall 3 regions of operation. The cutoff, the linear region, and then the saturation region. And basically, that is also what are the parameters. We just discussed the Kn prime, which is the transconductance parameter, then lambda, which is the channel length modulation parameter, and now the gamma, which is the body effect parameter. So we have to find all 3 of these parameters in the NMOS and the PMOS that we are testing. Okay, so I hope this clears up the relationship that we are going to observe in these devices. So now what we are going to do is look at the circuits that we will need to simulate in LT-SPICE first, and then actually build in the experiment for this lab. So first, I'm going to go over the NMOSes. So the symbol for an NMOS, it usually looks like this. So here you can see that there are 4 terminals. On the left, you have this line that represents the gate layer or gate terminal. And then there is a gap between this gate line and this line. that signifies that there is an insulation inside this device that electronically or electrically separates or insulates the gate from the other three terminals. Then in the middle, you have the body terminal, and the other two terminals are source and drain, these two. But as I said, that you can use them interchangeably. But in the symbol, look for an arrow in one of these terminals. The terminal with the arrow is your source. Um, so we are going to use that terminal for our discussion. Okay, sorry about that technical glitch. For here, for the NMOS, we are going to put this arrow over here. That means this is our source terminal and this is our drain terminal. And for the PMOS, I'm going to draw um, the circuit symbol. So you have your gate. This is your source. This is your drain. And this is your body. And again, the arrow signifies that that is my source terminal over here. Okay, so for the for the experiment and for the simulation, let's draw the circuits first. So you have your NMOS here. We are going to use a small resistor, RD. That is, you can choose any value between 10 to 15 ohm, which is just going to help limit the current in the drain source channel. And it's also going to help you measure the current because to measure the ID current, you can just measure the voltage drop across the RD resistor and then divide it with the RD resistor value. And that way you can get the current directly. So we will need a voltage source at the drain terminal. Let's call it VDS. We are going to ground both the source and the body terminal. And then on the gate terminal, we will add another voltage source like this, which is our VGS. So we are going to do a DC sweep analysis. So for the DC sweep, we are going to sweep both VDS and VGS. And we are going to observe what the current IDS looks like with respect to VDS. So ideally, I just drew it a little bit ago that our IDS curve will look something like this. So when you are changing the gate voltage, we are going to use three different gate voltage, 1, 3, and 5 volts. And we are going to sweep the VDS from 0 to 6 volt with a delta of 0.5 volts. So for that, we are plotting VDS in the x-axis and IDS in the y-axis. So for a particular VGS, let's say this is VGS is set at 1 volt, we will get something like this. I'm using like a qualitative plot just to show you the shape of the current. It's up to this point, it's the linear region, and then it saturates. Then when you increase the VGS voltage, you will get a higher slope over here. But the shape of the ID-VD curve will be the same. Then if you increase it even more, you will get a even higher saturation current and higher slope in the linear region for the MOSFET current. Okay, so that's pretty much how you want to do this experiment for the first part. For the second part, what we are going to do is check the body effect phenomenon. And to do that, we need, again, this is our drain, this is source, this is gate, and you have body. But now you need a voltage source between the body and the source terminal. And what we are going to do is we are going to remove the voltage source at the gate, and we are going to replace it with, we are going to connect that gate terminal directly to the drain terminal. And the rest of the circuit will remain same. You have your RD, and then you have VDS. And now we are going to do the same sweep, 0 to 6 volt with a delta of 0.5 volts. And for VBS, we are going to apply 0, 2, and 4 volts. And then measure the IDS current with respect to the voltage VDS or VGS. So if you plot VGS and IDS for different VBS biasing, what you see is provided in your handout. You will see something like this, like 3 different plots for 3 different body voltage, biasing voltage. And we call it VGS. As you can see, like G and D are shorted. So it's basically a dropped voltage of the VDS minus the dropped voltage at the RD register. That's the voltage is between gate and source. So you can derive the gamma value from these plots. Again, from the first part of the experiment, we derived the Kn prime value and the lambda value from that IDVD plot, IDS versus VDS plot. And from this IDS versus VGS plot, we can derive that value, the gamma value. You can also use the root over ID versus VGS plot to get this parameter, which is explained in detail in the handout. Now, for the PMOS, our connections are going to be changed a little bit. So let's draw the PMOS first. So in your textbook, you will see an alternate symbol, which looks something like this, with a bubble on the gate. That also says that it's a PMOS. The NMOS will not have this bubble here. And then the arrow says which one is your source terminal, and then the other one is drain and body terminal in the middle. So for now, we are not going to draw the bubble just to match your handout, lab handout. So for this one, you have to add a negative voltage in your gate, which is going to be VSG. You can see that I wrote this in a different way. Instead of writing VGS, I wrote VSG. You can do that, or what you can do is you can write it you can choose the polarity of the voltage source, minus on the above and plus on the ground, and then call it VGS, which basically means you are applying a negative voltage at the gate terminal. And then you have your body and source tied together. And then you have the drain and another source, which is V. And then its polarity is also going to be opposite. Give me 1 second. All right. So will have a voltage source which is VSD. You can write it in this way, then the polarity will be positive, negative here. But for now, we are going to write it in this way, VDS. All right. So we are applying these to voltage, and the ranges are similar from 0 to 6 volt with the delta of 0.5 volts, and the VGS is going to be from 1 volt, 3 volt, and 5 volts. And then this is my source and body terminal. This is drain terminal. We have a similar RD, and we can plot the IDS or ISD versus VSD. And then you will see the same shape of the ID curve in your PMOS. You can choose to do IDS, VDS, then your voltage, your current curve will go into the third quadrant because it will be a negative current with a negative bias voltage. If you don't want to do that, if you want to match the NMOS IDS versus VDS curve, and then you can do this in this order. Like you can choose ISD and VSD and to plot that. And these plots will have different VSG values, 1 volt, 3 volts, and 5 volts. All right. You also note that I wrote VSG instead of VGS because if you write VGS, then these values are basically negative voltages that are applied. Okay. And for the next part, the last part of this experiment, we are going to check the body biasing. So to do that, let's draw that circuit again. So this is source, body, drain, and just like the NMOS circuit, the gate is shorted to drain. Then you have a resistor and a voltage source that is connected here. And then here you have a voltage source between the body and the source terminal, which is then connected to ground, which just loops back to this ground here. So in that case, again, just following the NMOS example, you have a VBS or VSB value that is varying from 0 volt, 2 volts, and 4 volts. And then your VSD is going to vary from 0 to 6 volts with a delta of 0.5 volts. And the plot is also given in the handout, the kind of plot you're supposed to see. So you are plotting ISD versus VSG. And you will see something like this, similar to the NMOS IDS versus VGS plot. You will see a similar plot here for different biasing, body biasing voltage. Okay. Then you can derive all the parameters. So for the first plot, you will get Kn prime and lambda. And from this plot, you will get the gamma value. So that is pretty much all the experiment. In terms of simulation, you are going to use these circuits. You can simulate them in your LT-SPICE test bench. Build these circuits and then simulate them. You will need to add 3 library files that are already provided in the assignment page. Follow the instructions in the appendix of the handout that details what kind of library command or SPICE directive you need to include in your LT-SPICE test bench to run the simulation smoothly. And then you have basically, after you run the simulation, you can calculate the lambda, kn prime, and gamma values from those plots also. That is not mandatory. We are mostly focusing on determining the experimental value of these parameters, but you can do an initial check with those simulation values, whether they match the model parameters that are described in your model file for these constant parameter device parameters. If they match pretty closely, then there is a good chance that your experiment will be very quick because you will be more close to the simulated value or the ideal model values of these parameters. The last thing I'm going to do is draw the chip that you are actually going to use. So you are going to use two chips. One is an NMOS chip and another is PMOS chip. I just want to show you the internal device arrangement so that there is no confusion. There is also another setup file provided in the assignment page that shows how you connect these pins. You can look through that for reference. So these NMOS and PMOSs have 14 pins. I am just going to draw them first. So this is pin number 1, then 2, 3, 4, 5, 6, 7, then 8, 9, 10, 11, 12, 13, 14. So that's our NMOS. The code for that is ALD 1106. And it's similar to the PMOS. This is our NMOS. And it is similar to the PMOS, which is the code is ALD 1107. And it also has 7 pins. All right. So the way it's connected internally is that you have one MOSFET over here whose drain is connected to pin number 1. Gate is connected to pin number 2. And source is connected to pin number 3. And the body is connected to 4. So these NMOSs, there are 4 different NMOS in this one chip. So there is one NMOS here, there is one NMOS here, and then you have another NMOS over here. So all these 4 NMOSs, all of them has a body connection to pin number 4. So all 4 bodies are connected, shorted together and connected at pin number 4. And there is no connection in the 11 pin. You have the drain gate source arrangement on all the sides, like drain gate source, etc. And you can look in the handout. So you only need one device, one NMOS device here. You don't need to use the other 3 in this chip. And it's similar to the PMOS. The only difference is you have the body connection, which is a little bit different in the PMOS than the NMOS. So you still have 1, 2, 3 pin. They are drain, gate, source. But the body connection is in pin number 11. So this is pin number 11, which has the body connection. And there are 3 other PMOSs over here. They also have body connected to 11. Pin number 4 has nothing. Just like for NMOS, you have pin number 11. There is no connection there. So you also see the same thing over here in the PMOS. So once you build this circuit, you only have one external component, which is a resistor, and then 2 sources that you're going to sweep. In simulation, you are just running this sweep analysis. And in the experiment, you're also doing that sweep manually and just recording the current through that ID terminal, the drain to source terminal. And once you do that, you basically get the compare the values of the parameters. So that's about everything about this experiment. The final goal is to find the experimental value of these MOSFET parameters. I hope you all understood what we discussed. If you still have questions, just email me or post it on, just meet me in during the lab hours to discuss that issue. Thank you so much. Have a good time.